Hi there. Today we're looking at Accelerating Deep Learning by Focusing on the Biggest Losers by Angela Jiang et al. This paper is pretty simple, pretty short in idea, and is pretty much an engineering paper. So we'll go over this idea and give it a good look and discuss advantages, disadvantages, and so on. So what's the basic idea? The basic idea is the following. If you train a neural network, what do? Usually you have a training data set, which I represent here. Each line is a sample. And usually you have your network has a bunch of layers. So each line here is a layer of weights. What you do is you group your training data set into mini batches. Let's say that's a mini batch, 4 samples, and you pass it through the network. This is called the forward propagation. You then calculate the loss. So loss of your forward propagated signal, and then you backpropagate this loss. Now when backpropagating, you want to backpropagate the loss such that it reaches each of the layers and it tells each layer how to update itself. So what you want to do is, for each layer you actually need to backprop the loss once towards the layer below it and once towards itself, in order for the layer below it to continue the backprop and for the layer itself to update its weights. So each time you backprop, basically once towards the lower layer and once towards yourself. And that's a lot of work. So you see, whatever work you have passing your samples through the network here, whatever work you have, you basically double the work going back. And that's the core idea of this paper. Is, if you look at the following, in a traditional training neural network, you'll have some overhead in each training step, some overhead of maybe putting the data to the GPU or something like this. Then you have a time that you require for a forward pass, and then you have a big chunk that you require for the backward pass. And you see it's about double the size of this forward pass. And this paper asks, how can we reduce this backward pass time? So what they propose is the following. They propose, well, if the backward pass is expensive, and we do it here for each data point in these mini batches, why don't we stop doing this and only kind of try to select examples that are important? And once we only have selected the important examples, only those examples get to do the backward pass. Thereby, let's say if we can only select 1/3 of the examples to do the backward pass, we can reduce the amount that's required in the backward pass, the amount of work, by 1/3. Or, sorry, by 2/3. And the way they select the important examples is by looking at the loss. So they basically say, whichever examples have a high loss, these must be the important examples. These are the hard examples. And if we only train on the hard examples, or if we train on the hard examples more, then the network will learn on these hard examples faster. Of course, there is an implication there that if your network is good on the hard examples, it's also going to be good on the easy examples. That's like the definition of hard and easy examples. Of course, that's a kind of a simplifying assumption. But so the idea is only select the hard examples and by how much loss they have, and only then backprop these hard examples. And that's how they can reduce this by a lot. Now there's several intricacies here. So the setup time, of course, is the same. What they do next is they forward propagate the entire mini batch here, because they need the loss of each example, and then therefore they need to forward propagate the entire mini batch. At the end of this, they select the examples with the highest loss, and they only use those in training. Now training consists actually of another forward pass, but this one is much smaller because you only forward pass the examples that you're actually training on. And then the backward pass accordingly will also be much smaller, because now again you have less samples to actually train on. Now, the reason that you even need this second forward pass is the following. When you do backprop, you can't simply start with a signal back here and then backprop that through the network. That doesn't work usually with most network architectures. Namely, what you need to do is actually, while you forward pass, you need to remember information at each layer. A good example of this is the max pool operation. So in max pool, what you do is you maybe have 4 pixels that are next to each other, and you select one of them. Now, you need to remember during the forward pass which one you selected. Otherwise, the backward pass won't work. You need to know which pixel to backprop through. And that's why at each point you need to remember information to inform the backward pass. Right. So that's why basically you need a second forward pass with only the examples that you want to train on. So you forward pass once, calculate this loss, select the ones with the high loss, then forward pass these again, and then backprop only these examples. That's the main gist of it. This is exactly what you see here. So forward pass everything, then forward pass those again that have high loss, and then backprop them. There is actually an interesting thing in this graphic, in that you see that this forward pass here also is shorter than this forward pass, and I assume that's because this forward pass here actually needs to do those additional saving of information, while this forward pass here is simply a forward pass without intention of backward passing, and you can instruct the deep learning frameworks to then not remember this information. All right, then they have another improvement over their algorithm called stale selective-backprop. So this is called selective-backprop. They have stale selective-backprop. What stale selective-backprop does is it says, well, we might not always need this forward pass, right? What we might be able to do is actually, so first we take the entire data set. Let's use a different color here. Let's use this. We take the entire data set, forward prop it through the network, and then save into some database the losses, right? And then we use these losses to select the individual points here for a while. All right, so we perform maybe this is training here. You start here, you do this loss calculation, and then you run your training until a couple of epochs, and then you say, okay, now this information here is really outdated, I should really update it. And you do this entire thing again, and then you run training some more until you again stop and say, okay, now this information is stale again. Thereby you can amortize the cost of these forward passes. So you pass your entire training set once in a while, and then use those losses to select the hard examples. And that's amortized. You can then reduce this forward pass that's used for selecting again by a lot. And of course the paper shows that this doesn't hurt your performance too much if you have this stale information. Right. So this is the entire idea of the algorithm. And the algorithm is detailed here. So very briefly, you have this buffer, and you go through the data. You forward pass every example. For each loss, you calculate the probability that you should retain it. So it's a probabilistic framework. It's not absolute cutoff. If you decide to choose it probabilistically, you append it to this buffer. If this buffer is of a certain size, then you do the backprop only on this buffer. And this buffer now only has the high loss examples, or the high loss examples with higher probability. And don't forget, within this backward here, there is also an implicit forward pass. And then you clear the buffer and go on. So there's lots of, you see there's lots of forward passes here to compute the losses, and then every now and then there is a backward pass whenever the buffer is of certain size. Now the probabilistic calculation of how and when to retain a sample is very simple. You have a deck, of recent losses, a history of recent losses. You simply calculate the percentile that a given loss has in this history, and that percentile will then decide on the probability if you raise it to a power, and that looks something like this. So what's often used in this paper is this 33% selection. That would be the blue curve, and you see the median example here. If you are in the median, then you have about a 33% chance of being retained. If you have a higher loss than that, then your probability rises. All right, so the first interesting thing actually is this graphic here, where they show what the algorithm deems the hardest and easiest examples. So examples chosen least frequently, and this is the CFAR10 dataset, which is images 32 by 32 in color, and you need to classify them into 10 categories. And you see the easiest images, the ones chosen least frequently, are almost all automobiles. And of the automobiles, they're almost all where you see the full car with the wheels and whatnot, like this one here. So these are what the algorithm deems easy samples. And if you look at the hard samples, examples chosen most frequently by Selective-Backprop, it's these here. So it's, for example, bird. And bird, in this case, is just kind of a smear. They're just kind of smears on a blue background. It's understandably that at this resolution, it's pretty hard to make out that this is a bird. Airplane and automobile here, you see that it's only a partial view of the thing. It's not like the full car like we saw in the easy pictures. It's only partial. And this seems to be pretty hard, and it's understandable. This cat here, to me, it's even unclear if this is a cat or a dog. And I think dog is also a category in CFAR10, so the algorithm is certainly understandably confused by this example and deems it a hard example. And here, even more, you see truck. And this isn't a truck, as far as I can make out. These are two humans on the picture with no truck anywhere visible. So this seems to be a mislabeled example, and of course mislabeled examples are going to be of high loss to the algorithm. And this is the kind of first criticism or thing, and the authors recognize this, that if you upweigh your examples with high loss, you are going to upweigh all the mislabeled examples as well, and thereby you're going to train more on the mislabeled examples, and thereby you're going to possibly degrade your test performance much more than had you given every sample the same weight. And the authors address this actually nicely by doing an experiment. And the experiment is, what if we artificially mislabel examples? How much can these algorithms tolerate? And so they often have these graphics here where they show test error over time. So test error, and the x-axis here is number of backpropped images, which is kind of a time dimension in training these algorithms. You see the blue is a traditional model, and the pink is a selective backprop with a 33% retain rate. So you see the selective backprop is much faster in reaching a low error, and this first thing is simply with 1% of the labels shuffled. So 1% of the images are mislabeled. Selective backprop is still much faster than the traditional trajectory. If you go to 10% shuffled, still you can see selective backprop is faster, reaching a low error. Of course, the error now generally is higher. But if you go to 20% here, what you can see, 20% shuffled labels, what you can see, it starts to become clear that these selective backprop, it retains 33% of the hardest examples, right? So, and 20% of the examples have a wrong label. That means most of what it upweighs are wrongly labeled examples. Almost, let's say. That there's still a lot of correctly labeled examples. But you see, it gets to a low error, but then it gets up again as it kind of massively overfits on these wrongly labeled examples because it upweighs them so much. All right, it upweighs these because here still every example is hard, right? So these wrongly labeled examples, they'll get about the same weight as correctly labeled examples because the network isn't trained yet. But as you go lower, it starts to massively overfit. So compared to the traditional model, kind of just reaches this low error that is now corrupted by these wrong labels, but it doesn't hurt as much. So that's kind of my first criticism. If you have a lot of noisy labels, if you have a lot of mislabeled examples, then this method might actually hurt more than it helps. But the level is interesting, that it can kind of tolerate 10%, but it gets kind of into trouble at 20 or so more percent. So this is the first criticism, and that's how the authors address it. I really like this ablation study that they do. Here, this is kind of the meat of the experiments. So what they show here, these curves on the bottom, and let's look at this curve, is on the x-axis you actually have wall clock time now. So how much time do you need in order to reach a kind of low error? Here is test set error. You see the traditional model in blue has a certain trajectory. Now cath 18 is a baseline. Don't worry about it. What we're interested in is the Selective-Backprop, which is the pink, which you can see outperforms this traditional training. And what we're also interested in is the stale SB. So stale meaning it has this buffer of information that reduces, it's supposed to reduce the time again. And you see that even more outperforms the traditional approach. You can also see that the staleness here apparently doesn't hurt the performance too much. You see the error is fairly close, and it reaches this error in a much faster time. This on CFAR10. They have this nice table up here where they show the speed up to reach a given error. So what they do is they take this error of the traditional model, this test set error, and they ask how fast are these methods in reaching this error times a constant, so times 1.1, times 1.2, times 1.4. Now, of course, the reaching 1.4 times the final error is easier, and thereby, but it's also easier for the traditional model, of course. So that's the catch. But these are kind of benchmarks they chose to how fast are these models in reaching 1.1, 1.2, and 1.4 times the error of a traditionally trained model. And you can see here on CFAR10, for example. Actually, let's go to SVHN. SVHN is the easiest of the data sets, and it shows the most clear thing. So the traditional error is 1.7%, and you see that the speed up is so this Selective-Backprop is 3.4 times faster in reaching this 1.1 times the error of this traditional model, and it's also 3.4 times faster reaching 1.2 times, and it's 3.5 times faster in reaching it 1.4 times. The stale Selective-Backprop is even faster, so 4.3, 4.9, 5 times faster in reaching 1.4 times this reaching 1.4 times the error. And so what you can see here is that these methods really make it faster, but also there's kind of two important things to note in this table. First of all, you can see as you go to the right in the table, the speed ups get higher. And what it means is that as you make the problem easier, so as you need to reach a higher error, which is as you need to reach a higher loss value, these methods are there faster. what that means is they're really fast at reaching a somewhat decent point, which is represented here. They're really fast, but if they need then to reach a more and more accurate performance, they themselves get slower and slower. So this is of course clear, because what you're doing is you're no longer treating every data point the same. You are introducing a bias into your training by only training on the hard examples. So you're introducing a bias, and this bias will give you a speed up but also hurt your performance. And thereby, if you have to get more and more accurate, you will lose much of that speed up, because you need to reduce that bias at the end that you introduced. So that's the first caveat. As you want to get to a higher and higher performance, these methods will help less and less, because they basically introduce the bias to gain speed at the beginning of training, or to reach less accurate points. The second thing is, as you look at these problems here, so SVHN 1.7% error, CFAR 10 is a slightly harder problem, 2.9% error, and CFAR 100 is really a harder problem, where a traditional model has 18% error. If you look at the speedups now, then you can see, even at this rightmost end here, you have the 3.5 and 5x speedup. Here you have a 1.5 2x speed up. Here we have a 1.2, 1.6x speed up. So as the problems get harder, and as the kind of models get fancier, as the classes get more, then the speed up is much lower. And I believe that's because the bias you introduce by reweighing the samples, the bias you introduce will hurt you much more on a difficult and large problem with a large network than it will hurt you on an easy problem, right? Easy problem, you are fine introducing some bias, but if you have a hard, noisy problem, then this bias you introduce will hurt you much more, and thereby this the speed up that these methods give you is much, much less. And so this means that the performance of these models is directly anti-correlated with the hardness of the problem. And that tells me, it kind of makes it almost unusable, or it goes towards, if I look at the numbers over here, and extrapolate that to something like ImageNet, it tells me that these methods are going to be almost useless on a dataset of the size and complexity as ImageNet. And the interesting problems nowadays are very much in the domain of more hard, more complex problems. So the kind of usefulness of this method in practice is something that I wouldn't bet on just from reading this paper. I'm open to be convinced otherwise, but just from reading this papers, it seems like the harder you make the problem, the less these methods help, and that's exactly not what you want. You want exactly the opposite. You want to say, oh, if I scale this up, it'll give me even more of a speed up, and that's going to be even better. But this is the opposite. So and given that they have basically no theoretical analysis of how much this bias hurts you, or how you can still make it kind of good in expectation, how you would need to correct at the end, and so on, I would first, of course, test it. I'm very interested to see tests on larger, more complex problems. But from this, I'm a bit skeptical. I'm sorry. Yeah. So they show that on these datasets it clearly helps, it clearly speeds up the training, and that's, of course, that's already a good thing. And they do the required experiments, they do the ablation studies on these datasets, and so on. So you can see here, for example, on these first graphic, on all the datasets, see clearly it goes down as you introduce the more sophisticated algorithms, but again, you can see on the hard data set it doesn't go down as much. All right, but they do discuss this. They're really fair to themselves. They do discuss this in their paper of how how practical this is and so on, and what else they tried and didn't work, and that's I think that it's a really good paper in itself, and it's a really good investigation. All right, so that was it for me. Have a fun day. Bye bye.